students. Myself Chandrasekaran. I am working as assistant professor in EC department. Today I am going to handle the topic on flip-flops. So flip-flops is one of the sequential circuits. So first, what will be sequential circuits, right? So sequential circuit is nothing but if the input is depends on the present inputs. Okay, so the input and it's a memory element. So one combination circuits, it will be inputs and this will be outputs. Okay, in a combination circuit, the output is depends only the present inputs, whereas in a sequence circuit, the output is depends upon the present input and the past output. So the past output, it will becomes as a memory line. Okay, so this memory will be used as a flip-flops. Okay, so for a basic element, the flip-flop is a 1-bit memory storage. So flip-flops, so flip means 1 and flop means 0. So only it called as 1-bit memory storage element. Okay, so here the flip-flop will be divided into 4 types. So first one will be SR flip-flop, and second one will be JK flip-flop, and third one will be D flip-flop, and fourth one will be T flip-flop. Okay, so SR will be a first basic element. From SR we may derive D. After that JK. From the JK we can derive T flip-flop. Okay, so let me see first one, the SR flip-flop. So first one will be SR flip-flops. So S means here S is set, is a S, R for reset. So set and reset flip-flop. So here the logic diagram for this SR flip-flop will be, I will draw the logic diagram for SR flip-flop using NAND gate, right? So yes, and whenever I am going to the sequence circuits, the clock will be used for a synchronization between the signal. So here a clock will be used for synchronization between the signals, right? So here I am using S and R, set and reset. So there will be a NAND gate, using NAND gate, and after that one more NAND gate. So this will be a Q and this will be a Q bar. So the Q bar will be feedback into this line. So this is what the sequence circuit logic, right? Similarly, Q will be feedback into this NAND gate, right? So whenever I am using the only NAND gate, it will be as a combination circuits. So whenever I am using the output will be feedback into the input, it comes under is a sequence circuit, right? So Q and Q bar will be output, and S and R. So here S will be set and R will be reset, and here the clock. Okay, so consider the clock frequency. When in a system, the system operates in a 1 MHz clock frequency means, so what it denotes means, so clock frequency will be 1 MHz means, so F equal to 1 in 10 power 6. Okay, so T is equal to 1 by F, therefore 1 divided by 1 in 10 power 6 is 10 power minus 6 seconds. That's called as 1 microseconds. So in the clock signal, the time period for the on and off will be 1 microseconds. It may be equally divided for a duty cycle. If a 50% duty cycle means, so on time and after will be equally divided. So 0.5 microseconds and 0.5 microsecond on. So this is the clock signal, right? So in this clock signal, it may divide into 2 types. It will be level triggered clock signal or edge triggered clock signal. So we may level trigger means for the 0.5 microseconds will be fine on time. After 0.5 it will be off time. This will be a level trigger. For as edge trigger, it will be divided into 2 types. So positive edge and negative edge trigger. So positive edge means, so when 0 to 1, so on, it will be a positive edge, and 1 to 0 it will be called as negative edge. So mostly we are using negative edge trigger flip-flop. here we are using the positive edge in SR flip-flop. So for that we can assume this clock will be 1 here always. Okay. So now we go for S and R and Q. So we will write the function table for it. So function table for SR flip-flop. So how the function table tells about how the SR flip-flop work as a flip-flop, right? Here input will be 3 inputs. So what will be 3 inputs? We have here the clock will be a always positive edge. So always we can, it's called as positive edge trigger, and the input will be S, R and Q of N. This will be Q of N will be a present state. So in a sequence circuit, the output will be defined as present state and the next states. So here Q of N will be a PS, is a present state. Okay. So present state, and Q bar will be a complementary state, right? So present state and Q bar. So that the input will be SR and Q of N. So 3 inputs will be there. So Q of N, S and R. So in this case, so 3 input would be possible, means the combinations of a combination input bit 2 power 3 will be 8 combinations will be possible in a digital electronics. So here 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1. So totally 8 combinations, 0 to 7. These are the possible combinations for flip-flops. Okay. So we may derive the function table. So the output will be, we can also call it as Q of N plus 1, or it's also called as next state, right? Next state in S. Okay. So we will assume that, so Q of N present state will be 0 and S will be 0 and R will be 0. This is the case. S will be 0, R will be 0 and Q of N will be 0, right? So whenever I assume that the Q of N will be 0, so Q bar must always 1. Okay. So complementary state, so it's always 1. This is our present state, and 0 and 1. So before going to this flip-flop logics, so we must know the NAND gate truth table, right? So NAND gate truth table, so when A, B, C will be output, means 0 0 0 1 1 0 and 1 1. So 0 0 means output will be 1, 0 1 means output will be 1, 1 0 means output will be 1, and 1 1 will be output will be 0 for a NAND gates. So this is what I apply in a flip-flop. So when the present state will be 0, the 0 will be feedback here in this way. So now first comes to the first flip-flop, 0 and 1. So output will be, what will be 0 1 will be, output will be 1. Similarly 1 and 0, output will be 1. Okay. The feedback input will be 0 and 1. What will be the output? So it's nothing but 0 1 will be, output will be 1. Okay. This 1 will be feedback here. So 1 1 will be, output will be 0. So when I am assuming the present state will be 0, the next state comes as, it's called as Q of N plus 1. This will be a 0. So this is what I am mentioning here, 0. Okay. After that, the next case, the same 0 0 and present state will be 1. I assume that the present state will be 1. So the 1 will be, so if I consider the present state will be 1, the Q bar will be 0. Okay. So the 1 will be feedback here, right? So for a 0 0, the same option will be there. The clock will be 1. So same option will be performing here. So 1 1 means output will be, so 1 1 means output will be 0. Okay. So 0 will be feedback here. 0 is feedback. So 0 will be feedback. So 1 0 means output will be, what will be the 1 0? The NAND gate will be 1. So I assume the present state will be 1. The next state will be also comes as a 1 when I am given input as 0 0. So whenever 0 0 I am given, S will be 0 and R will be 0. So the present state will be the same state present in a Q of N plus 1. Okay, 0 or 1. Okay. Similarly for the next states, right? 0 1 and 0 1. So here S will be 0 and R will be 1. So assume that the state Q of N will be 0. Q of N will be 0. Okay. So 0 will be feedback here. And now 0 1 means what will be the state here? 0 1 means output will be 1, 1 1. So 1 is clock, so 1. So 1 1 means output will be 0. Okay. So 0 0 means output will be here. The assumed case will be 0 1. So 0 0 means output will be 1. The 1 will be feedback here. 1 1 will be output will be 0. Okay. So present state 0, next state also 0. Okay. So similarly, the next case we can calculate. So we can know the logic function of the flip-flops. So here present state will be 1, next state will be 0. The 0 1 will be same. So 1 will be here. So 1 0 means output will be 1 0 means output will be here 1. Okay. And 1 1 will be feedback. The output will be 0. Okay. So in this case, I assume that present state will be 1, but the next state will be came as a 0, right? So whenever I am setting the state will be 0, or will be 1. Here or will be is denoted as a reset. When reset will be 1, the output whatever the present state is there, 0 or 1, the output came as a 0. Okay. So in this way you may calculate the same functions. So here for 1 0 set will be 1. So whatever the input present state will be 0 or 1, the output will be as like a 1. So consider the case last 7th case here. S will be 1 and R will be 1. The clock always we can 1, right? The Q of n, the state will be 0. So if the present state will be 0, next state will be 1. So the Q bar, this complement state will be 1. Okay. So here the Q of n will be feedback here 0. So what will be the output of this first NAND gate? So 1 1 means output will be 0. Okay. Similarly for the first NAND gate 1 1 will be output will be 0. Okay. So 0 0 feedback 0 0 for the 0 0 NAND gate, the output will be 1. The 1 will be feedback here. What will be output? 0 1 means output will be 1. And 1 will be feedback here. Similarly 0 1 means output will be 1. And 1 will be feedback here 1. 0 1 means output will be 1. So all the states the Q will be a 1 and Q bar also 1. So whenever the present state 0, the complement state always 1. But there is a case S will be 1, R will be 1. What will happen? The next state, the output will be same state as a 1 and 1. There is no complementary. This is called as indeterminate state. Okay. So I am defined as a X here. Okay. Similarly for the next case, if I am assign the same S and R and Q of n will be 1 and Q bar will be 0, right? So 1 1, the same case 0, here also 0. The 1 will be feedback here. 0 1 means output will be 1 and 1 will be feedback here. 0 1 means output will be 1. So 1 will be feedback. So similarly the same 1 1 will be persistent. This is called as indeterminate state. So there is no complement state is get in a output side. So it's called as indeterminate states. This is the function table for the SR flip-flop. We may derive this from this function table. We may write the characteristics table for the SR flip-flop, right? So characteristics table will be is nothing but for the given input what are the outputs, right? So characteristics table means so S R will be the inputs and output. So what will be the output for the case? So for the two inputs possible, the 4 components will be there. 2 power 2, the 4 components will be present, right? 0 0, 0 1, 1 0 and 1 1. So whatever the states, so when I am given the input 0 0 inputs, okay, 0 0 case. So what is the, what am I getting the output? When I am given the 0 0, Q of n will be 0, Q of n plus 1 will be 0. Similarly for 1 and Q of n plus 1 will be 0. This is called as same state. If the present state is equal, the same state for the next state. So I am defined here. It's called as Q of n. Whenever the input will be 0 0, the output will be the present state and next state equal. So I can call as Q of n is called as no change state. We can define as no change. Shortly we can call it as NC, right? So only we can output will be Q of n. When for a 0 1 states, present state will be 0, next state will be 1. So output Q of n plus 1. Whenever the what are the states 0 or 1, so output I am getting as a 0, because so reset will be here 1, so I am getting 0. So whenever the 0 1, the reset will be set into 1, so output will be 0. Similarly for S and R, set will be equal to 1, so whatever the present state in a 0 or 1, the output I am getting as a 1, so it is called as set state 1. So the condition for the 0 0 means Q of n will be called as no change state, and 0 1 will be it's called as reset state, and 1 0 will be it's a set state, and 1 1. So what is the case for the 1 1? If I am given S and R will be 1, if I'm, what is the present state will be 0, I am getting as a XS. Why I am getting X? The same state. So if it is a Q will be 1 and Q bar will be 1 and Q will be 0, Q bar will be also 0. This is called as indeterminate state. So it's called as, well, whatever these, where I am given S will be 1 or R will be 1, I am getting as a XX. This is called as indeterminate state. So from this is a characteristic table. From this function table, I may derive the characteristic table, right? So now we may derive the characteristic equation of the flip-flop from this function table, right? Okay. So for this derive the functions, we may go for a K-map. This is a Karnaugh map. We have 3 inputs and output will be Q of n plus 1. So I may rub the characteristics table. So characteristic equations, it is derived from this function table. So Q of n plus 1 for a K map, the 3 variable K map. So S will be here and R Q of n will be upper table, upper column. Here 0 and 1, 0 0, 0 1, 1 1 and 1 0. So we may place it as 0 1 2 3 4 5 6 7. This is what the K map representations. So I may mapping the Q of n plus 1 table, right? So the characteristic equation for output is called as Q of n plus 1 is the next state, right? So Q of n plus 1 will be output. So what is the case for 0 0, right? The combination, this will be 0 1 2 3 4 5 6 7, right? So for a 0, output will be 0. So we didn't mention the 0 in a K map. So next, for 1, the output will be 1. For 2, it will be 0. We didn't mention. And 3 will be 0. And 4 will be 1. And 5 will be 1. And 6 and 7 will be called as XX. So when we grouping here, so it's a 4 variable possible. So 4 combinations will be grouping. And for 1 and 5 will be grouping here. So what will be K for the equation for Q of n plus 1? I am writing here as for the 4 for quad groups, it will be as S. Okay, for the 4 group it will be S. For 1 and 5 pair group, it will be S R dash Q of n. This is the characteristic equation of SR flip-flop. So if you given the 0 0 for the first case, S will be 0, R will be, if I am substitute the 0 here, so R will be 1, Q of n will be 0. What will be the output I am getting? 0. This is what, so we may derive the function table from this equation also. This is what we can relate. Either we may derive from characteristic equation to the function table or function table to the characteristic equation. Okay. So this is a characteristic equation. Next we go for a excitation table, right? So what is the difference between the characteristics table and excitation table? Characteristics table is nothing but from the input I may derive the output, right? Whereas in a excitation table, so it is a vice versa technique, right? From the output, what will be the input? I decide what the output will be, what is the input I may given for this particular flip-flop. This is for the excitation table. We may derive here for the excitation table. Next. So excitation table. So for the excitation table, what are the possible for the inputs? Because the output will be the input, right? So Q of n and Q of n plus 1. So this is a present state and this will be a next state. Okay. So what are the input possible here? S and R. So for the two possible input means, so the combination will be 2 power 2, 4 combinations will be there. So 0 0, 0 1, 1 0 and 1 1. For a 0 0, what is the logic behind is, when the present state 0, the next state will be 0. So what will be the S and R? So consider this function table, present state 0, next state 0. So what are the, which combination it will be arrived? So for the Q of n, this is the combination, right? So 0, present state 0, next state 0. So next, where the possible? Here itself. So I may derive here, I may denote for 0 0, present state 0 and next state 0. For the corresponding, what will be the inputs? So S and R. Okay, this is what S and R. So for present state 0, the output will be for S will be 0 and R will be 1. For a present state 0, next state 0, the S will be 0 and output will be, so 0 0 S combination S and R, and here 0 1. So the two possible combination will be arrived for S. The state will be present state 0, next state 0. This is a combination. So S will be 0, R will be 0 and 0 1. So I may write this combination as 0 0 1, we may call it as X. It's a don't care. So I may write this function table as excitation table in for X 0 int X, 0x for present state 0, next state 0. Similarly for 0 or 1, present state 0, next state 1 means what are the combination will be arrived in the function table? Present state 0, next state will be 1 and there is no combination, right? So present state 0, next state 1. So for this state, the SR will be only 1 and 0. So for the S and R 1 and 0, you may get it as a 0 0 1 combination, right? Present state 0, next state 1. Similarly for 1 and 0, what other combination will be possible? 0 or 1. So 1 0 and here 1 0, the 0 1 will be a possible here, right? So only I am writing here as a 0 1. After that 1 1, present state 1, next state 1. So for this combination I may define here present state will be 1 and next state will be 1 and here present state. So for this combination I may get 0 0 and 1 0. So 0 0 1 0 SR combination. So I may write this combination as X0. So I am write here as X0. This is for excitation table. Okay. So we may derive this function table. From this function table we may write the characteristics table. From the function table we can write the excitation table. Okay. Thank you.